Okay, let's work. So again, I have the lecture helper screen going. And I'm not yet graceful with handling your online questions here. I'm not yet sure how that's going to affect the way I interact with you. So we're all figuring that out. My current mechanism is to see the questions and to try to tailor my narrative so that I think your questions are answered. I'm pretty much never going to say, oh, hey, who asked? How would we write the second example, Z and Y, with just one line? I'm probably never going to, make the direct connection to the questions. I'm going to try to weave in the answers, and we'll see how that goes. You guys are late. But it's okay. I forgive you. I forgive you. Thank you. Thank you for coming. That's what makes me happy. Okay, I actually do have a few announcements. Number one, the honors section for the course is beginning next week. You're going to have to feed me this one. Next week, next Monday, 5 to 6:30 in Siebel, what room? Basement, 0216. Do we have the stadium room? Okay, 0216, okay? And there's room in the class. So this is a web mechanism for fulfilling the James Scholar requirement. You can sign up for an HCLA if you're in LAS. That's like more acronyms than I don't know, makes me feel powerful or something. Or you can just do it for the interest. It's 1 credit hour and it's starting now, so it's not too late to do a late add if you'd like to. Our intention is to use data from the world around you to help you create nifty data visualizations and have you help us figure out other cool things that we can do with this data. So you'll be doing some actually visualization design as well. Should I say anything else? Okay. Lecture helper is live. That's the other thing. Anybody want to send me a test question? Please. Maybe it's not live. Can you send? It is? Can you send me a test question? Oh, lecturehelper.c. What is it? Okay. Uh-oh. Yeah? The question is, can you audit the honors course? Why? Because you don't have a credit hour. Can you fix that? Do you know how to fix that? I don't know what I did. Yeah, that's what I tried. Okay, I can do it from there. Thank you. Okay. So yeah, I guess you can, but you'll have to make us put your name on the roster if you wanted to. Okay. The very last thing is I meant to announce this on Monday because I'm quite embarrassed by it actually. On Friday, lots and lots of things were left in this room, including a water bottle whose owner is found, and a graphing calculator. I'm not going to tell you the model. You have to tell me. And a lifeline, a cell phone. So if you left any of those things in this room last Friday, come see me. Okay. So I want to bring us back to where we are here. I'm going to bring us back to where we are content-wise. Now, up until last time, we had two different ways of using memory. We could use memory kind of as a variable, right? And that had a name, and we knew how to access it and change its value. Or we could use memory in big contiguous chunks. What kind of name would you use for that? What would you call memory that comes in big contiguous chunks of various values? An array, right? That's an array. Contiguous chunks of memory that can store lots of different values. That's just an array. Last time we introduced this new notion that allowed us to take memory in little bitty bits and chain them together. Now the picture that I drew for this looks something like that. I can't reach it. I have to, I wish I were Peter Pan, then I could fly around. Okay, the picture that I drew to denote this setup looks like this, and I kind of referred to it as chained memory. And what I meant by that was we keep track of, we typically call it head, we keep track of the memory address of the first block, and within that first block or that first node, we keep track of the memory address of the second block. And within that block, we keep track of the memory address of the third one. Okay? Now, I like to think about this as sort of a scavenger hunt through memory, right? Because we give you a starting point, a variable head, and it has a value. That value tells you where to go to find your next thing. You get there, you get your next thing, and a note that tells you where to go to find your next thing. Now, you could be racing all over town, or all over memory, to find the values of this structure. Now, something should strike you about that. It should feel like it would take you longer to navigate all of that than it would to navigate your data if it were in sequential positions in memory or in an array. So just as a fundamental structure, this chained memory should feel a little bit slower because those things are all over memory. Now, it turns out not to matter that much, but just there should be an instinct behind it. And you'll learn more in other classes about why this behaves more slowly and in which context this behaves more slowly. Okay, so let's see. Any questions about that so far? Any questions? Okay. All right. So now pretend, just a minute, Mark. Let me keep going. So now pretend that we have this head and we're holding on to this whole chain of memory, and that's what we know. We have that variable. Okay. We can't get to the 2. Well, how do we get to the 2? I should be asking you that. How do I get to the data that has value 2? How do I get there? How do I get there? Yeah, Nick? I have to traverse the list. That's right. And I have to start at the head to do it. The only window into this list is via that first thing. And my only mechanism for getting to, the fourth thing on the list is to walk past the first one, use it to get to the second, to the third, to the fourth, etc. Okay? Now, the need to do that is so frequent that we're going to design a little helper function that we're going to deploy anytime we need to get around on a structure that is composed of these linked nodes. Okay? Now that function we're going to call findKth. It's not a member function of a particular class. It assumes that we have list nodes and that we can use a list node pointer as a parameter here. So our intention is to be able to call find kth, I'm going to put it right here, an example of the use, actually I'll do it like this. An example of the use of find kth is list node pointer k equals find kth from the head, and we're going to walk that many steps forward. So I'm going to say 3 steps forward. And our intention here is that K would be a pointer pointing to this. Okay? Is that clear? Where 3 means take 1, 2, 3 steps forward in the structure. Any question about that? I have a check for understanding. What do you get if you do dereference of K? What do you get? You get 2? No, you don't. You get a list node whose data element contains 2. So if you dereference K and say data, in this case, then you get 2. Okay? All right, let's see. There's one other little piece of specification about the way this find kth function should work. If K is bigger than the length of the list, you should just return null. Okay? All right, so let's write this function. Let's see. I'm going to write it recursively, and let me tell you why. I could write it iteratively, right? Like it's a process of just walking down the list. I could write it iteratively, but here's the thing. When I write iterative code, I open myself up for having an off by 1 error, right? Like, oh, should I take that step this time or not? And, oh, does this all happen before the while loop conditional? When I write iterative code, I make off by 1 errors a lot. So what I would like to be able to do is handle the base case, because that's easy, and let the recursion determine how many iterations it needs to do. That is, how many steps it needs to take. Now, in this example, we probably could get away very easily with doing this iteratively. But I'm just saying in general, for me, now, I'm not imposing it on you, but for me, it's easier to think about questions like this recursively. So, what's the base case? This is the case where no steps need to be taken. What is the base case then? If K is equal to 0, right, there's another situation where we don't want to do anything. And that is, okay, so negative values of K, I'm going to assume we're not going to get any. We're only going to get positive values of K. If our list is empty, right? If head is empty, that's the base case, right? We're doing this on nothing. We better not have to do anything. So if her is equal to null, then in either of those cases, we are going to return the value of cur. Okay? So if there are no steps to take, or if there are no steps to take, it means we have positioned cur in the right spot. We should just return it. If cur is null, we've walked off the end of the list, or we've got an empty list, and we should just return null. Okay, that's what we're going to do if K is bigger than the end of the list, okay? Otherwise, we're going to return the find kth of, help me with the parameters, please. cur next. I'm dereferencing cur. Is that okay? How do I know it's okay to dereference cur there? Because I know cur isn't null, right? If cur were null, I would be in the other part of the if statement. So dereferencing cur is cool. Okay, and the other parameter is k minus 1, that's right. All right, so this is kind of cool because cur next, when I do cur next, I take the step, and by passing k minus 1, I record the fact that I have done so, right? It means I have one fewer step to take. Any question about that? Is it okay? Yeah? So the question is, how do you determine when the list is empty, and how do you know, or how do you determine the difference between when the list is empty and when you haven't found the kth one because you can't, because you're at the end of the list? Well, guess what? I know the end of the list is an empty list because I'm representing an empty list as null. So I could cover up that whole slide. Okay, I'm gonna do that. I could cover up all of this. Okay, and here's the current chain, right? It's an empty list. So what you're suggesting is actually those two things, I don't want to distinguish between them. They're the same. Yeah? Yeah, okay. So I'm going to throw that back at you. So what if I wanted to distinguish between those two cases? Like, oh, your K is too big, knock it off. Versus it's just an empty list. And the answer to that is simply that I would break apart that conditional, right? I would, if K is equal to null, or I'm sorry, if K is equal to 0, I'd do one thing. If cur was equal to null, I'd do something different. That's all, okay? All right, any other questions about this? That's a really good question. Any other, yeah? Oh, so the question is one of, what if it does this? Then K is never going to be 2. Huh. And then your base case. Huh. Then it's just K equals 0. You don't have to worry about it being null, right? You're always going to be able to find it. It's just an issue of how many times you walk around. That's like an interview question, isn't it? Yeah, okay. Determine whether your list has one of those. That's an interview question. Okay, any other questions about this? All right, I'm going to erase that because it's not, it's extra, beyond the scope. Okay, I love the next question. That is, what's the running time of this function? Now, it's a little bit hard to answer because it depends on, what does it depend on? K, right? Oh, the analysis. So the running time depends on parameter K. If you happen to know that K was always 4, then it's a constant time function, right? You know you're never going to have to look at more than 4 nodes, no matter what. But it isn't that. The way you evaluate running time is to take your worst case running time, which is almost always what we do, is you take your parameters and you pretend like your worst enemy is choosing them. Okay, so in this case, the worst possible value for K is anything greater than N, right? N or greater. In either of those cases, and where N is the length of the chain, in either of those cases, the running time is going to be proportional to the length of the chain. So we say that the running time is big O of N. Do you remember the other words for how we describe big O of N? Linear time, that's right. And we argue it by simply saying, look, the amount of time that it takes to walk to a particular position relies on a constant amount of work per node. So you're doing the same amount of work per node, okay? Or a constant amount per node. All right, any questions about that? Is it okay? All right, I'm going to consult my okay, I have little quizzes for you, okay? They're kind of backtracking a little bit. Where is head stored? Where is head stored? The fact that I could give head a name, the fact that I could say where is head means it's on the stack, right? All variables with names are on the stack, okay? Now, where is head's target depends on how we built up this chain. It will be eventually a constructor's response. Right now, the way we did it was to deploy insert at front. And if you recall from last time, insert at front used new to make a new one of these nodes. So each of those are on the heap. So head is on the stack, but the memory that it refers to is all over the heap, okay? And likewise for the rest of them. Let's see. All over the heap is an operative phrase. Okay. I want to get back to this question. How long does it take to find the kth thing in an array? Give me array element 4. Give me array element 52. Give me array element 4,000,052. Same amount of time with some little assumptions about how that array moves into memory, okay? We assume a random access model which says we can access the values of an array in constant time. So for the purposes of this class, if we're looking for the kth thing in an array, well, that's just R of k, well, maybe -1, right? Yeah? And that happens in constant time. So if I were you, I'd be sitting there thinking, well then how come we're even talking about this linked memory if we've already seen an example of something that arrays do way better, right? We can get to any one of them in constant time. Why are we even talking about this thing that requires us to walk down in order to find elements? Well, keep that question in the back of your mind until a little bit later. I want to switch gears for a second and give you some vocabulary. The vocabulary is abstract data type. An abstract data type is you can think of it as a document. It is a description of the functionality of a data structure. Okay, so let me write that down. We commonly refer to it as an ADT, and it is the description of the functionality of a data structure. This data structure is some configuration of memory. Okay, we're going to see some. So an array is a data structure. A chain of linked memory is a data structure. Okay, we're going to see a bunch more. The ADT is merely an interface, a description of how something, whose name we might not have yet, how something behaves. Our very first abstract data type that we're going to talk about is ADT list. Now, What is ADT list? Well, it's likely to be this functionality that underlies any of many different applications, like your to-do list, or your list of favorite movies, or your grocery list, or I don't know, your friends list, any of many different lists, this ordered collection of things that you have in your life have underlying it this, this abstract data type that we're going to refer to as list. Now, the one that I'm presenting to you is a little bit artificial. I've crafted it for this example. There is a list in the standard template library. It's also an ordered collection of things, but it has a more complex interface. I have simplified our interface. And the nice thing about C++ is it basically takes the ADT and it uses it as the class definition. So this is actually why it's really nice to use C++ in this course, is because we have this beautiful way of talking about our ADTs, okay? So, for example, my ADT list is implemented in class list, and it has the following functionality. I can create a new one, I can get its size, I can remove and insert, and I can get an item from it. Okay, so I can return a value from a particular location. Okay, that is the ADT. That plus probably a little bit of documentation is ADT list. It's a description of the functionality. I think the very best way for me to show you how my ADT works is to take you through my little example code, okay? So here I declare one. And then the first thing I'm going to do is start inserting into it. So we're going to insert into position 1, value 4. Then I'm going to insert into position 1, value 6. What should happen to 4? What should happen to 4 if I insert 6 in position 1? Here's a way to think about it. So this is an artifact of this particular list ADT. But here's a way to think about it. Suppose 4 used to be your favorite movie. What's your favorite movie? Do you have a favorite movie? No? Do you have a favorite? Everybody think of their favorite movie because it could be you next. What's your favorite movie? Flip? This word right here, flip? Okay. Okay, so imagine that this is your favorite movie, okay? And then you see The Princess Bride. What happens? Duh, right? Flip is no longer your favorite movie, but it doesn't get replaced. It gets moved down. That's how my list ADT is intended to work. We'll talk about the standard template library one later. Okay, so 4 gets moved down, and 6 is placed in front of it. And then you see Inception. I don't know, who knows? And it goes here. Now you see, okay, what's a third? Then you see Shawshank Redemption. And it goes in position 3, okay? So I think what happens then is that 4 gets bumped down and 0 goes in there, okay? I got to leave the movie thing. I'm not quick enough to figure that out on my own or on the fly. Okay, now this one is a little more complex. It says get the value in position 2. So the get item demands a location. So get the value of the thing in position 2 and insert it into position 4. Okay, so I think what that means is that I'm going to insert 6 there, which happens to move 4 down. Okay, any question about that? And now just to kind of close this off, if I say get size, what do I get? The number of things in the list, so it is presumably how this would work, and so I would get 5. remove removes the thing in the second position. So now what's in the second position? 0, good. And then get item 3 returns 6. All right. So this is how my list works, okay? To communicate this really, truly effectively, I would not only give you the interface, I would also document each one of these things very carefully, like we do in the specs for your MPs. Okay, any questions about this or observations? Any questions? I think if I were you, I would have some questions. You like this? Is this okay? Okay, yeah? Yeah. The same is true for Java. It's true for Java too. Any class-based system that allows functionality inside the class definition. Python, same. It's object-oriented, but it's really C with classes is really my comment about it. It's not pure object orientation. Okay, yeah, Mark? Can you guys hear him? Okay, so he says, why does your list start with the first thing? Why does the list start with position 1? Raise your hand if you all had this kind of concern. You kind of wanted it to start at 0. Raise your hand high if you wanted that list to start at 0. You really wanted me to say 0 there instead of 1. Okay. So here's the thing. We're kind of the only people for whom this would be an issue. It's our problem, right? If you go out of this room into the broader world, you might have to go south of Green, but if you go into the broader world and you start talking about the 0th, what's your 0th favorite movie? People are going to be like, oh, you are such a geek, right? This is our problem. The point of this observation, the point of the observation is kind of an aside. And the aside is that you, as brilliant programmers, are responsible for making your interface easy for the client to use. So if you're talking about something with a general understanding, like a list, where if you said, give me the first thing on your list, they're going to look at the first thing, right? I mean, it's English. It's not even CS, right? If that's who you're writing code for, then your interface should behave that way. Okay, so that's what drove my cringeworthy selection of 1 as the first thing. Okay, so that's the design for the client little snippet of a talk. Now, I have a story that goes along with this, and I think I'm going to tell it to you because why not? It'll probably be the last time I ever tell this story, like last time. So, here's the story. When I was 7 years old, my parents moved our family, my hippie parents moved our family from Southern California, where you could get good guacamole and tacos at 2 o'clock in the morning, and there were record stores and radio stations and my relatives and all the stuff, pro basketball team, like all the stuff of Southern California, and they moved us to western Nebraska, about as close to Wyoming as you can get, actually. Yes, to western Nebraska, where there were no tacos. There was nothing at 2 a.m. and no tacos ever. They put ketchup on their tacos. Ew is right. Okay. Yeah, it's bad. No radio stations. Well, there's KRVN that had the Forum Report, right? Like, so I thought that, and no Grammy, right? My relatives weren't there. So I thought that this was like, I was completely, I was shook for a really long time. Plus, everybody in the second grade class, they're all cousins. I'm not even kidding. It's like, it's really an issue of like how far, they're all cousins. We take that for granted, but then how, what's the least common ancestor is the real question. It's crazy. Yeah, it gets better because my dad, my dad's a good dad. He went through this list of reasons we should be glad to live in western Nebraska. One of them is sledding, really good, we actually had snow there. And another one that he used to me when I was 7 years old is he said, the Cornhusker football team is number 1. Okay? And to this day, I remember being that child and going and wanting to say, but Dad, who was number 0? So what I really think is that I was destined to be part of this community. Like it started early. All right. That you can, I'm sorry. Yeah. I'll reconnect us. I'm not sure it's worth it. I'll never tell that story again. All right. What'd you do in class today? Slide 3. Okay. Don't look at that code. All right, so we're getting a little bit more, so we've designed for the client now. Now we need to get a little bit more detailed about our responsibility, which is implementation. Now, it isn't so nice in C++ that you can also look at the interface and see a lot of information about the implementation. So take a peek and tell me how you feel about my implementation of the list class. Number 1, how would you describe what I did here? How would you describe my implementation of the list class based on the private members that you see? And the other clues on the screen if you like. What is it? It's an array, right? You all see that it's an array? Is it a special kind of array? Static array, that's right. This is an array on the stack. How big is it? Does that ever change? No, it's a static array. The size of it never changes. So this is a really bad, already we see that this is a really bad list implementation. This list implementation should be a list 8 implementation, right? Because you can't, or at least we haven't provided a mechanism for making this list any longer than this. Heck, this list is shorter than the number of things you have on your to-do list for this class, much less your whole to-do list. So this is probably not such a great list implementation. But I want to use this implementation to illustrate one of the pitfalls involved in using arrays at all for this particular interface, okay? So pretend like our list, we're really trying to implement a little list class or a short list class. And what I want to be able to do is implement the insert function. So what I want to allow is that in my list, I insert into position 1 value, 152. So you can see what it is, and assume that we already have inserted 46038, say. Okay? All right, so now, what's my plan here? What's my plan for inserting into position 1 value 152? What's my plan? I need it to go right there, right? Is there space? No. I have to make space. And moreover, that I have to make space thing occurs wherever we do the insert. I was just sort of choosing the worst possible place because the way that we make space is we have to scoot the 4 over. But in order to do that, we have to scoot the 6 over. But in order to do that, we have to scoot the 0. To do that, we have to scoot the 3. To do that, we have to scoot the 8. So let's do that. 8 goes here. 3 goes here. 0 goes here. 6 goes here. 4 goes here. And now, all of a sudden, finally, actually, I should say, I have room for 152. Do you like it? No, I don't either. The implication is that shifting the value ran in time whose running time, whose total time is proportional to the size of the list, or big O of n, or linear time. And the way to see that very clearly is that if this list had 1,000,000 things in it, we would be shifting for a really long time. Okay? All right, any question about it? Also notice that I evaluated this running time based on the worst possible input parameter, right? If instead we had inserted at the end of the list, well, that would have been easy. We just need to keep, it's just at size, right, in the last position. But no matter where we insert, we have to do some shifting, okay? Any question about that at all? Is it clear? Okay, hold on just a second. Notice that that's why there's a while loop in there. And that code is so ugly, I really don't want you to look at it. It really does that I just suggested. And it only works if there's space, okay? So don't look, don't look. All right, any other questions, any questions about this? Yeah, did you want to ask a question? Okay, but maybe remove is easier. Is remove better? Is remove better? I want to remove the third thing. I want to remove that 6. Uh-oh. Now we have a gap, right? Now we have to close up that gap in order to know where the next thing is. Otherwise, we're effectively implementing linked memory inside the array. Okay? Did you have a question, Bert? So the question is, what happens if we try to do the insert function and there's no space left? My code ignores the request, so it's bad, bad code. A better implementation would resize the array and make sure there's room for it. So either one of those two strategies, you take your pick of the favorite of those two. It's reasonable to resize the array so that the client doesn't know that you've run out of space. Okay? All right, anything else about this code you have a question about? Okay, so this is going to model, what we're going to do all semester long. We have looked at an implementation of the list class, and we're kind of sitting here going, I don't like it very much. And so we're wondering if there's an alternative to implementing the list class. What else might we use to implement this list class? What do you think? Yeah? Yeah, a linked list or this chained memory. And now we are going to start calling this thing a linked list because we have this idea of a list. So if that's the case, if we're going to implement this thing at using linked memory or a linked list, what do you think the private members look like? What do the private members of the list class look like? Have you started MP3? Yeah, okay, so what do the private members look like? It's just a pointer, that's right. In this case, it's going to be a list node pointer. Okay, so let's go take a look. I was going to go through a million examples of shifting, but you would fall asleep. Okay, cool. So now I have what I assert is a better implementation. Now, that may not be true. It may not be better, but I'm going to at least investigate it analytically to find out if maybe it's true. It's certainly an alternative. It's certainly very different, a different implementation of this list class. Okay, so just as you suspected, we do indeed have a head that we're going to keep track of. Okay, it's going to be our handle on that list. In MP3, things are a little bit different. I believe you also have a tail, so there's a pointer at the end. Moreover, in the list node class in MP3, rather than just being able to walk forward on the list, you can also walk backwards, and you can go back and forth. So you have bi-directional pointers in every list node. We're not going to do that here. We're going to only focus on singly linked lists in class. All right, so we've got a head, a list node pointer as the head. We don't know what the fourth one is, but we've got a hold of it, we're sure. We know how many elements are in the list because we have this size that we're going to maintain. That is, we're always going to increment it when we insert into the list. And now we have these two other things, and they are private. Why? Why did we decide that find and list find, which is implemented just like find Kate, I believe. Oh yeah, look, it looks the same. Oh, except they're switched. Yeah, there's a bug here. Why are they private? Really good. That's exactly right. We don't want the client to know anything about our implementation. We want them to only interact with the interface. They know how to do that. It's designed for them. It behaves exactly like they anticipate. If we give them find, we don't know how they're going to use it here. And in fact, this version of find won't even work for the client. Why? Why won't this version of find, if I made it public, why will the client still not be able to use it? Yeah? There's no way to access it. Well, the find function can, right? Because it'll still be a member function. It'll just be a public member function. But they will have a list. They will have a list object. And that thing will contain data, which is its own head. Okay? So they will have access to the head because find will be a member function of the list class. So it will know where it starts. Oh, they can't call it. You're saying they can't call it. Right, right. They can't call it because they don't know where the first thing is. But the reason is not because they don't know where the first thing is, because they do. They can ask for it, right? It's because they don't know what type of thing that first thing is. They don't know anything about list nodes at all. So the fact that find has as its first parameter a list node pointer, and moreover, that it returns a list node pointer, and list nodes are private, they're only for internal use, it means the client cannot use that function. The client cannot use list nodes. Okay? Is that clear? Sorry to have misinterpreted your suggestion. All right, is it clear? Yeah? Mm-hmm. So they can create a list. The client can create a list, but they don't get to know what that constructor does. They don't get to know what memory looks like behind that list thing. I can throw this right back at you and say, how do you think a standard template library vector is implemented? We don't know, right? And yet we're pretty sure that within 3 seconds we could go look up documentation and be using one effectively. Okay? All right, we'll pick it up here next time. Notice we got through 5 slides today and we only skipped 1.
So I'm the student who sent you an email this morning asking got an exemption that I didn't like clear.